All right, let's talk about this exam. Is that right? Yeah, okay. Can you all see that? Not really, huh? A's, B's, C's, D's, F's. Class average was a 57. Standard deviation was 20 points, which means that the grades were pretty spread apart. Highest grade was a 92. I know that's hard to read. 92 was the highest grade, and the lowest was a 24. So this is passing. So you can see we have a majority of the class was underneath passing. I haven't done anything to the grades. They're just the raw grades. Not quite sure how I feel about this. Obviously, it's not encouraging to see that, but I don't know. I mean, there were some students that did well, and that always, kind of, if everyone were down here, I'd have some sort of, thoughts about whether or not the exam was maybe too hard or too long or something, but we had students complete the exam, within the time frame. I don't know, what do y'all think? Any thoughts? I'm disappointed, yes?
How do the midterm grades usually look for this class?
Well, I used to have a policy that you had to get a 50 or higher on the midterm and the final, because I give so much work take home that you still had to come in on the midterm and final and perform at least 50%. So it's actually, I was going to show you all this. My old syllabi for my old classes says you must have a 50 or higher on the midterm and the final in order to pass the class. Like if you don't get a 50 on the midterm or final, then you don't pass no matter what you do for take home. Now that's not in this syllabus, so you don't have to worry about that. Historically, I don't know, it's been better than this, but I've also had a lot of students that kind of take their foot off the gas at the end of the semester after they've already done all the take homes and their grade, they're comfortable with it. They kind of ease up at the end. But this is a little bit concerning for the midterm, for where we are. I don't know. I'm not sure. Only you know how much effort you put in. If you put in a lot of effort and you got a low grade, and that's probably discouraging for you, but only you know how much effort you've put in. What I kind of am concerned about is that I have not had a lot of participation with the take-homes. I've only had a few students turn in take-homes. And so I have a real question as to whether or not students are really doing their homework. And if you're not doing your homework, then this is what I would expect to see. If a majority of the class isn't doing their homework, I would expect to see a majority of the class not do well on the midterm. And I don't grade homework, so it's totally on you. I guess I could ask you to see your homework, right? That looks like a half question over there. No? No. So, I don't know. Yeah, I wish we were in here like, yay, everyone did great. So these exams are what, 15% of your, no, 25, is that right? I looked at it earlier. The take-home exams are worth, I believe, 45. 45%, I believe. And then I put in there that you keep a binder, right? And that's 10%. You can get 110 in this class. So I'm concerned that because I've made so much of the grade take home, so much of it like, not these tests, that there's maybe not as much emphasis. I could be completely wrong. I don't know. I don't know how much people are putting into this work. So, yeah. It is what it is. I'm not going to curve the grade or do anything like that. I feel like it was doable. It's basically the same test I've been giving for a couple of years in this class. So I've seen classes do well on that test. So, all right. Well, can we be positive attitude now? Can we move forward? Yeah. Okay. All right, so I recommend you go through the test. You come in, you sit down with me, we go over any questions you have. If you feel like you did something right or you want to know what the right answer is, I didn't put the answers down here for you. I'm not going to give you the key. So if you want to talk about the exam, just come into my office and we can just go over the exam. It's up to you. Remember, I'm in my office before this class from 10:45 until class starts. All right, well, I hope you all had a good spring break. Yeah? You're all rested and ready to go now? Everyone's excited? All right, well, we're going to pick up where we left off. And I know it's been a long time, but do y'all remember this Lagrange thing we had talked about? Now, this was not on the test, right? We did not have this on the test. So when we were doing Lagrange, when we started, what we had done is a couple of examples using this basic idea that, where is it? That if you had a function of two variables, which to us is like a surface, and you had a constraint equation, that you could find the maximum of that surface on the constraint by setting up these equations and trying to solve like a system of equations. So in the problems that we already did, we had to figure out what x, y, and lambda were. Does that sound familiar? Okay. So we had done a couple of examples in class, and we stopped with that one right there. And now we're moving on to the next idea, still in the same section, and that is what makes Lagrange multipliers so great. And that is that it extends to functions of more than two variables. You can use this method for functions of 3 variables, 4 variables, doesn't matter how many variables. And so that's where we start. So let's say we have a function of 3 variables. Keep in mind that if we have a function of 3 variables, that means we cannot visualize this. It's not a surface anymore, right? You have 3 inputs and 1 output. So you have to have 4 dimensions to try and visualize this, which is not really possible for us to do. So we have some function of 3 variables, and we're constraining it to some constraint equation where the left side is some function of x, y, and z, and then the right side is some constant. So in order to find the maximum or minimum values of that function of 3 variables constrained to that equation, we have to set the gradient of f equal to lambda times the gradient of g. And then we also have to make sure that that constraint equation is satisfied. And when we do that, we wind up having 4 equations and 4 unknowns. So when you do the gradient of f equal to lambda gradient of g, that means gradient of f, that's what the gradient is, equal to lambda times the gradient of g. And then you set these components equal to one another. And that's where you get these 3 equations, and then you have the constraint equation. So now 4 equations, it's going to be messy. So let's do this here. So let's see, how can I try and get you to see what the heck we're doing here? Let's just look at this function right here. F of x, y, z equals 8x minus 4z. Let's just say, and this may not even really make a whole lot of sense if I try and plug numbers in, but let's just say that this function tells you the temperature of, like if you move to some point in three-dimensional space, you give me an x, a y, and a z coordinate, I plug the x, y, z into this, and it tells me the temperature at that point. Okay, so let's just say that's a temperature function. And so you have all these different temperatures within the space. What it's saying is if we take this temperature function and constrain it to this, now what is this? This is g of x, y, z equals a constant. But physically, what is this? This should look familiar to you. It's not quite a sphere, like an ellipsoid, okay? It's like an ellipsoid. It's like an egg, right? Just the shell of an egg. These were those quadratic surfaces we were talking about. So what this is saying is, okay, this is your temperature function. Give me x, y, z, I give you the temperature, right? But this is saying you can only be on this eggshell. So if you're only on that eggshell, if those are the only points you're allowed to be on, then at what point on that eggshell is your temperature the highest and lowest? Does that kind of make sense? So instead of just being anywhere in three-dimensional space, you're constrained to this shell. All right? So the way we do this is we try and satisfy the four equations. Okay, so let's do that. So what I want to do is I want the gradient of f to be equal to lambda times the gradient of g. So what is the gradient of f? Let's go ahead and just calculate the gradient of f. It's a vector, right? So the gradient of f is 8. That's the partial of f with respect to x. And then comma, partial of f with respect to y, 0. And then partial of f with respect to z, which is -4, right? So that's a very clean gradient, because it's a bunch of constants. Now, what's the gradient of g? Let's just do that here. So remember g, this right here is g of x, y, z. So the gradient of g would be what? 2x, 20y, 2z. Okay, so now let's set up our equations. We need this gradient of f to be some scalar multiple of the gradient of g. So this is where we match these up, right? This, create our four equations here. So equation 1 is the equation that the partial of f with respect to x has to be lambda times the partial of g with respect to x, which means 8 must equal what? Lambda times 2x, or 2 lambda x, however you want to write it. Okay, that's our first equation. Our second equation says that partial of f with respect to y has to be lambda partial of g with respect to y, which means 0 has to be 20y times lambda. So, and then our third equation is partial of f with respect to z must equal lambda partial g with respect to z. -4 must equal lambda times 2z. Okay. And then we have our fourth equation, which is what? The constraint, right? This. All right. So there we go. So we are trying to find a quadruple, basically. We're trying to find an x, y, z, and lambda. Now, we saw like a couple of weeks ago that the lambda doesn't really matter in our final answer, but really there's 4 equations and 4 unknowns. So is there anything that we can do here? Is there anything easy that we can see? Equation 2 forces something right away, doesn't it? This basically means that lambda has to be 0 or y has to be 0. So let me look at that. Lambda has to be 0 or y has to be 0, right? That's from this. Now we have to look at each of those scenarios. So let's start with lambda being 0. All right, let's just start with lambda being 0. If lambda is 0, then what other information can we gain? Is there anything else we can gain?
Then equation 1 wouldn't work if lambda was 0. Because that would equal 0. That means a equals 0.
Yeah, that wouldn't make any sense, would it?
Yeah.
Equation 1 wouldn't make sense. And this wouldn't make sense either, right?
Lambda can't.
So lambda can't be 0. Make sense? So if lambda is 0, equation 1 would become 8 equals 0, which isn't true, right? So therefore, 3 dots, right? Therefore, lambda cannot be 0. All right, so what does that mean? That means that y has to be 0. If we have any hope of finding where we have x, y, z, and lambda that make all 4 of these true, then we know that that can't happen, so that has to happen, right? So if y is equal to 0, let's see what we can get from that. Well, if y is 0, we know that one's true. Y is not here, is it? Y isn't here. Now, if y is 0 here, we have an equation with 2 variables in it, don't we? If y is 0, this becomes x squared plus z squared equals 5. Now, why is that useful? Or how is that useful?
Because we don't want another variable in here?
Yeah, it would be nice to get this down to 2, right? So if you have this with just x and z, look at this right here. This has z in it, right, in lambda? So you could solve that for lambda, couldn't you? And then you could solve this for lambda, and then set them equal to one another, couldn't you? And then you'd have an equation with x and z connected, which would then allow you to come back here and substitute in for one of the x's or the z's. So it's going to take a little work, but we're going to get to it, okay? So first thing, let's let y be 0. Now, if y is 0, let's just keep in mind that equation 4 then becomes what? X squared plus z squared equals 5. All right, that's what we know. If y is 0, we've got this is true, right? Further, equation 1 says that lambda must be equal to 4 over x. Now, we have to be careful there because we just divided by x, right? Which means x can't be 0, right? But are we all comfortable with the idea that x can't be 0 to begin with? Like if x is 0, this equation's not true anyway, right? So we don't need to really consider x being 0 here. Like we never have to go back and say, well, what if x was 0, right? Because if we did that, well, this is not working. With me? So this is okay. And then also equation, which one? 3, lambda is negative 2 over z. And again, we don't have to worry about z being 0 because if z was 0, this wouldn't make sense. So that makes sense to do dividing by the z. Now set them equal to one another. So you get 4 over x equals negative 2 over z. And you can kind of cross multiply. I'm running out of room. This is one of the drawbacks to trying to fit everything on this board. But I'll just come back up here. Okay, so what does that tell me then? 4z equals negative 2x. And I guess we can say negative 2z equals x. So I can replace x with negative 2z now, can't I? And I can go back into this equation, replacing x with negative 2z, and then I'll have an equation for z that I can solve for z, right? So let's do that. So back into equation 4, we get negative 2z squared plus z squared equals 5. And what's that? 4z squared plus z squared equals 5? Which means 5z squared equals 5, which means z squared equals 1, which means z is plus or minus 1. All right, Does that all make sense? All right, so now what?
Make sure that it works for all the equations.
Well, does it work for all the it should, because we started out by saying y is 0, so we know this is satisfied, right? Right, and then we use these two equations to come up with a relationship between x and y. And now we use that relationship to get this equation to be true. So we know that this equation is true. We actually need to look at each of those cases, like if z is 1 and then versus if z is negative 1. So we're going to get two different answers here, aren't we? So let me continue this right here. Okay, if z is 1, then what can you tell me?
Lambda equals -1.
If z is 1, lambda would be
Oh, I was looking at the original equation.
over here.
Yeah.
If z is 1,
Oh, I was reading
Right.
wrong, sorry.
you were doing that one?
Yeah.
If z is 1, lambda equals -2.
Yeah, lambda's, if z is 1, lambda's -2, right? We can say that?
Yeah.
What else can we say? X equals -2 also, because look, here's my relationship between x and z. So x is always -2z. So I'd have that. And then what's y?
Still 0.
It's 0, right? It was 0 through this whole thing. Do you see we've just created the quadruple? This is one of the quadruples right here. This is -2, 0, 1, and then the lambda is -2. So x, y, z, lambda. This is a place that I have all four satisfied. All right? We could check it, but we're going to trust that we've done everything logically here. If we plugged in these values for x, y, and z into all of these and lambda, we would get true statements. Now that's not the only one though, right? There's another important point here, and that is, what if z was -1? So lambda then would be 2, x would be +2, y is still 0. So all it does is changes the signs of lambda and x, right? And then we have another triple here. 2, 0, -1, and 2. Now, have we covered everything here? Is there another way that we can make all four true? Well, if we go back to equation 2, right, the only way to make equation true was lambda being 0 or y being 0. We said lambda couldn't be 0. That forced y to be 0, and we've already looked at all that, right? This is all based on y being 0. So there's nothing else you can try. You can't like let y be 1 or something like that. That won't work. This one won't be satisfied. So these are the only two interesting quadruples that we have. So what are we going to do to answer the question? Yeah, that's right. We're going to now say, all right, well, let's see what happens at these points. So remember, I'm only going to work with the x, y, z's on these. Right? Something is happening at that point. So if I go in here and I plug in 2, let's do the first one over there, -2, 0, 1, what would happen into the original function? Get 8 times -2 minus 4 times 1. So what's that? -12? -12? And then if we do the other one, f of 2, 0, -1, we get 8 times 2 minus 4 times -1. 16 plus 4 is 20. Do you all agree with my arithmetic? Okay. So that's it. The maximum value of this function, yes?
F of -2, 0, 1. Shouldn't that be -20?
Yeah.
Where?
-16
Oh, yeah.
minus 4.
Okay, thank you. -20. That's -16. Yeah. Check my arithmetic. You know I don't like arithmetic to begin with, but I've been on break, and you know, it's no excuse. But. So this function, constrained to that eggshell, this is the maximum value you are going to get, 20, and the minimum value that you're going to get is negative 20. And it's going to happen when you plug in this for x, y, z and this for x, y, z, respectively. Okay? And this point, negative 2, 0, 1, right? Somewhere that's like negative 2 on the x-axis, 0, and then up 1. That point is on the eggshell. You know that because it had to satisfy this equation, right? So it should, right? Let's plug it in. Negative 2 right here, we get 4. 0 here, we get 0. 1 here, we get 1. We get 5. 5 equals 5. So this point does lie on here, but it also corresponds to the maximum value of that function. All right, what do y'all think?
So,
Kind of get the idea?
can you differentiate, because we've been finding maximum and minimums for a while, so what's the characteristics specifically, just to review of Lagrange versus the absolute?
Okay, good question. Let's do it in terms of surfaces first, because this isn't a surface. So let's try and understand it in terms of a surface first. So if you have a function of two variables, we know that if you graph it, it looks like a sheet. And if we just talk about the implied domain of this function, so like if I give you a function, say 1 over x times y, that's a function of two variables. This obviously has some domain restrictions, like x can't be 0, y can't be 0, but otherwise you can plug in any other number. The only way to figure out what's happening here is to find local maximums and minimums, to find the humps and the valleys. And to do that, we go through the process of calculating that capital D, okay, which meant you do the partials, figure out where there's 0, then you do the second partials, fxx, fyy, fxz, or sorry, fxy, and then you calculate D. That'll tell you where you have, humps, valleys, and saddle points. Now it doesn't tell you absolute maximum or minimum. It's just local stuff. Now, if somebody comes and restricts this to a closed bounded region, which means you restrict the domain to, let's say on the ground, instead of plugging in everything, let's say you just take like a disk down here and you map that up here, and then you just get this region on here. There you can find the absolute maximum and minimum by using the other method, which was you have to work your way around the boundary, like the last problem on the test. And then to figure out what's happening on the inside, you do something similar to what you did with D. And you just kind of compare them all. Good so far? Lagrange, not this one, but Lagrange allows you to do the boundary part. Okay, so if you take a function of two variables and you restrict it to an equation, so here's an equation, that's a circle, isn't it? Then this would be your g of x, y. That's a circle on the ground, and then all you're doing is finding the max and min on this boundary instead of like on the inside also. Do you see the distinction between these three? Everyone see that? No?
I mean, you said didn't we find the max and mins at the boundary?
We did, but we had to go around the edges, right?
This is a different way.
This is a different way of doing that.
This way
Okay?
left to what, so we can do whatever shape with Lagrange. It's not because we're used to having to.
Yeah, see, the shapes with the other method where we would do like L1, L2, those shapes had to be really good. Like they had to be something we could work with.
But this one,
This one, it can be any curve down here. But what's even better about Lagrange is that when you take the whole idea of the surface away now, and you go to a function of several variables, then as long as you're constraining yourself to some constraint equation, you can still find the maximum and minimum, but see, now you're outside of what you can see anymore. So that's why I was trying to give you the temperature. It's kind of like this by itself gives you the temperature everywhere, right? Like you just plug in X, Y, Z. There's no restriction on the domain there. right? There's no restriction. So if I tell you what's the maximum minimum temperature, you're not going to have one with this one because you can just imagine if you just pick bigger x's, right? Let z be 0 and just pick bigger and bigger x's, you're just going to keep getting higher temperatures the further out you go on the x-axis. Make sense? But if we say you can only plug in points that live on this shell, then there is a max and min. And that's kind of like with this one, if we just go to the blue circle, there has to be a max and min here because this is a curve up here, some sort of weird shape along the surface.
But just like with the other method where we found the outside and then what's within, does this one only find like the border of our
This only finds the border, that's right. It's not allowing us to go inside and find, like if you had that egg and then everything in it. No, it's just the outer boundary. Okay, let's see what the one below, good question. I'm glad you asked because, I mean, I feel like I understand it, but I don't know sometimes if I'm getting it across properly. Okay, let's see here. Look at that one right there. So we'll go a little faster through this one. Again, we have some function that gives us, you know, maybe this function is now giving you the force of gravity at a certain point, or a magnetic force. Like you're sitting at a point, you give me an x, y, z, and this somehow calculates the magnitude of some magnetic force. It doesn't matter what it is. Something is happening at the point, and you're trying to measure it, and then you're trying to say what's the maximum and minimum value of that function if we constrain ourselves to what? What's that? That's the unit sphere. Yep. That's your sphere of radius 1. So I'm only allowed to be on the sphere of radius 1, and at every point on that sphere, I'm computing this. And now I'm asking what's the biggest and smallest it's ever going to be, right? Okay, so let's do this. First equation, I need partial f with respect to x to be equal to lambda partial g with respect to x. So what is the partial of f with respect to x? Be careful here. 2xy squared z squared. Yep, because you have to treat x, y and z like constants, but they're attached to the x through multiplication. So they come along, right? That needs to be equal to lambda times 2x. Okay, there's our first equation. Second equation is going to look very similar. Equation 2, partial f with respect to y equals lambda partial g with respect to y. So same thing, it's going to kick a 2 out, right? 2x squared y z squared equals lambda times 2y. Everyone good with that? Third equation. I don't know why I'm doing 1 equation 1, 2 equation, who cares? Okay, so 2 gets kicked out, x squared y squared z, lambda times 2z, and then finally our constraint equation, which is x squared plus y squared plus z squared equals 1. All right. What now? Ugh. What?
Just to simplify it all, we can take a 2 out.
You want to get 2's out of here? I'm okay with that. Get 2 out here. I wouldn't divide by x, but I don't know, actually. Oops. I took the y out. Can't do that. I have to be real careful because if I divide both sides by x here, I have to ask myself, could x be 0? You know, and I think x could be 0 here, right?
Yeah.
If x is 0 here, then that could be true so long as y and, z and lambda were 0, one of those. So we have to be a little careful with that. A little careful. Man, look at the left sides of these. Aren't they really like similar to one another? We've played a game like this before, where we can take each of those equations and then multiply both sides by something to make them all look the same. So I'm going to write this. If x is not 0 and y is not 0 and z is not 0, right? So suppose that the x, y, z's, none of them are 0, okay? None of them are 0. Then equation 1 can be rewritten by multiplying both sides by x. And if I do that, I'll get x squared, y squared, z squared, right? X squared, y squared, z squared equals lambda x squared. And what else? What am I going to do with this one? Do y'all see what I'm trying to do? Trying to make this look like that. Multiply by y. So if I multiply that by y, we get x squared, y squared, z squared equals lambda y squared. And then equation 3 will do the same thing. X squared, y squared, z squared equals lambda z squared. I can do that so long as these is x, y, z were all not 0, right? Can multiply both sides by x, multiply both sides by y, multiply both sides by z, and now all these look the same, so I can set these equal to one another, right? So let's work with these two first. That tells me that lambda x squared equals lambda y squared. Agree? Now don't divide by lambda. Let's move everything to one side. Let's factor lambda out. And then we have a difference of squares there, right? And so we have three possibilities here. The three possibilities are what? Lambda 0, or x is y, or x is negative y. Crap. All right. What else? What now?
You can apply that to equation 4.
Yeah, we could have, you mean we could use that information over there in equation 4? Like if I replace x with y or y with x, we could go over there and we could start getting less variables there. But see, I'm with you, but can't we also work with like the first one and the last one maybe? Like these two, I could use the same exact argument I just used here. That if this has to be equal to this, well then that also has to be equal to that. So I'm going to kind of hang tight here for a second. I'm going to say similarly, what would we get? We have lambda x squared equals lambda z squared. And if we do all the work for that, we're going to basically get down to lambda has to be 0 or what? X has to be z or x has to be negative z, right? It's basically the same algebra would take you to here. All right, let's start looking at some cases here. What if lambda is 0?
Then x, y, or z would have to be 0.
Exactly. So good. Let's start with that. Suppose lambda is 0. If lambda is 0, just look at the first equation right here. If lambda is 0, this side's 0. And these are three factors, right? And the only way that could be 0 is if one of those is 0, right? But we started this whole argument with x, y, and z couldn't be 0, right? That eliminates lambda. So if we start with this, we're working with this assumption to start all through here, then we got to lambda. What if lambda is 0? All we have to say here is that if lambda is 0, equation 1 becomes x, y squared, z squared equals 0, which implies that x equals 0 or y equals 0 or z equals 0, which is a contradiction. Have we done that? We've done that? Okay, so that's a contradiction. Therefore, lambda can't be 0. Okay, so if lambda can't be 0, now we have to look at these scenarios here. What if x is y? Start with that. What if x is y? And then over here, we have to pick one of these. X is z. How about we do that? All right, so I continue. I'm going to leave this up. I'm going to leave that up because we're still working under this assumption here. All right, so suppose x equals y and x equals z. So that's taking the two assumptions. I haven't looked at all the cases, but this is going to be real nice, right? Because what can I do if x is y and x is z? Equation 4 would then tell me, yeah, that you have x squared plus x squared equals 1, which means 3x squared equals 1, which means x equals plus or minus root 1/3. So I think we're starting to get some possibilities here. Let's start listing them out. What if x is positive 1/3, like root 1/3? Then what's y? Same thing, right? That's our assumption. And then what's z? Same thing. And then what's lambda? We could go in here and solve for lambda. We could go in here and we could plug in, x, y, z. But remember we said lambda isn't important in terms of the final result. So I'm just going to put in here lambda, okay, question mark, and I don't care. All right? There's a lambda that goes with that, though. All right, that's one thing that could have happened. What else could have happened? We could have had negative root 1/3, and then same thing, negative root 1/3, and then same thing, negative root 1/3, and then some lambda, and again, who cares? What are the only other possibilities? I mean, we've done this, right? We've done this right here. I'm sorry, it ends right here. Right? We said if x is y and x is z, then we get those two things. But we still should look at what? If x is negative y and x is negative z, right? But will it matter? Yeah, it won't matter because when we get in here, it's going to be the same thing, isn't it? When we square them, the negative is going to be irrelevant, right? And even more important than that is that, even if we go through, let me do it here. Suppose x is negative y, and let's say x is, we could go z or negative z, doesn't matter. There's actually like 4 different combinations we have here. X could be y, x could be z, that's one possibility. X could be negative y, x could be z, that's 2. We could have negative and negative, and then negative and positive, all the 4 different combinations, right? But at the end of the day, it does not matter because when you plug them in here, this is going to be the same algebra. And so when we come in here, what are all the different things we could have? You think about the different possibilities we could have here. We could have plus or minus root 1/3 here, plus or minus root 1/3 there, plus or minus root 1/3 here, and then lambdas for each one of those. Does this make sense? Like we could have every different combination of our x's being positive, this being opposite of it, or the same. But look, when this goes into the function, we have to test all these, right? What happens when we test them all? They're squared. They're all squared. Which means that we're going to get the same answer for every single one of those, aren't we? Okay, I'm not ready to do that yet, though, because I don't think we've exhausted all the possibilities. Have we? This was all under the assumption that x couldn't be 0, y couldn't be 0, and z couldn't be 0. So what if one of them is 0? Can that happen? Let's see. Are we good with this right now? This is kind of where we are. Yes? Okay. Yeah, I'm just going to erase all this. So now, suppose x is 0, y is not 0, and z is not 0. Let's see if that's even possible. Let's let one variable be 0 and see if this makes sense. How about your first equation? Is it satisfied? Yes. Okay. How about your second equation? So what would equation 2 tell us? What would equation 2 tell us? That 0 equals lambda y, which would mean what? Lambda is 0 or? Y is 0, right? Okay. What else? Is there anything else we get? That was from equation 2. What would equation 3 tell us if x was 0? Equation 3 would tell us that 0 equals lambda z, which would mean lambda would have to be 0 or z would have to be 0, right? I know it starts getting confusing, doesn't it? Okay, so let's see. If x is 0, the second equation tells us that lambda or y would have to be 0. Can't be this. Why? Because I said it's not, right? So it can't be this. But that would mean lambda would have to be 0, right? So if lambda is 0, then what do you get? Where are you going to get? Are you going to get a contradiction anywhere?
Except on equation 4.
How would you get a contradiction here? So we know this means z can't be 0, right? So lambda is 0. So I think this is where we're at. X is 0, lambda is 0. We got that? Okay, if x is 0 and lambda is 0, this is true. If x is 0, lambda is 0, this is true. If x is 0, lambda is 0, this is true. Okay, here, x is 0. So what does that mean if x is 0? So if x is 0, equation 4 tells us what? Y squared plus z squared must equal 1. All right, now what?
And y and z, if lambda is 0, then y squared plus z squared equals 1 would have an infinite number of solutions.
If lambda, yes, this is an infinite number of solutions. This is actually, remember we were restricted here to a sphere? This is like a sphere. This y squared plus z squared is a circle on that sphere, isn't it? All the points there. We're kind of jammed up here. Do y'all see that we're jammed up? Because we don't have anything else to be able to get what x or what y or z is, right? Because there's an infinite number of possibilities. But there's something that's going to save us. Anyone see what's going to save us? Yeah, look at the original function. What is our assumption here? X is 0, right? If x is 0, something interesting is happening, right? Something interesting is happening. But if you plug 0 in here, it doesn't matter what y and z are. You get 0. Does that make sense?
Yeah, and that can't be a possibility because that does not fall on the constraint, right?
No, that would be okay. We have, what we're saying here is that we have points right now that work. We have 0, right, for x. We have for y and z, all the conditions are is that y can be whatever it wants to be, and then z would have to be 1 minus y squared, and then we have some lambda. In other words, there's an infinite number of answers that would make this true, right? This is going to be true so long as y is y and z is, just solve that for, sorry, I'm missing a square root, aren't I? Solve that for z, solve this for z, move the y squared over, take the square root. You could even do plus or minus. Doesn't matter. There's an infinite number of interesting points where all of these are satisfied, aren't there? But because the original function is x squared, y squared, z squared, if we let one of these three variables be 0, it's not worth even looking at this because we know the function's value here. At any of these points, the function's value is 0. That one. That makes sense?
So that means still this.
That means that for here, if we plug this in, if we plug in f of 0 and then y and then square root plus or minus doesn't even matter, 1 minus y squared, plug it in the function, we get 0. And it doesn't, so that 0 is going to, I think, be our minimum value. We have to, remember we had those other points we had to check? Okay. Now, that's what would happen if x was 0, right? If x was 0 and y and z weren't. What if y was 0 and x and z weren't? Same thing. And what if z was 0 and these two weren't? Same thing, right? What if two of them were 0? What if the two of these were 0 but one weren't? Same thing, right? Now, could you have all three be 0? No, because if you let all three be 0, then this equation isn't true. So if I let one of these be 0, I have circles. Let that be 0, I have circle. Let that be 0, I have circles. So anywhere we have circles on this sphere, right, we have our sphere like this. We have a circle like that that's in the xy plane. We have a circle like that which is in the xz plane, and then there's another one, well, it's hard to draw these, but in the yz plane, the xz plane, and the xy plane, we have these three circles. They're all unit circles. And anywhere we have those unit circles, we have 0 as our function's value. Yeah? If I make two of these 0, then I'm going to be where? North Pole, South Pole. If I make those two 0, I'm going to be out here, out back there. Make sense? Like this is my x-axis. Here. But those are still on the circles, right? So we should get 0. So I don't think there's an easy way to like explain this other than to at this point say, you know, if one or two of our variables are 0, the function's value is 0. And we're done. Let's go and take a look at that one last one we have to check, which was this one, plus or minus root 1/3, plus or minus root 1/3, plus or minus root 1/3. Let's plug that into the function. We should get 1/3 cubed, right? Which is 1/27. Just cute, because of the original function, right? We square each one of those. That. So the maximum value of this function is 1/27th. And the minimum value of this function is what? F of 0, you know, question mark, I've already done that, is going to be 0. Or if we had any two of the variables be 0, it's going to be 0. And you could flip this 0 here, 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 flip them around, move them around, doesn't matter. All right, that's an interesting problem, huh? Kind of saved us, the original function saved us, didn't it? So you might ask yourself, well, what if the function didn't save us, right? Somewhere in the Lagrange, you would have been able to isolate the x, y, and z. It would have been possible. It's the inherent nature of this function is what caused that to happen. So the fact that we didn't kind of get lucky, just the algebra works out. the way it's supposed to. All right, can I move on? All right, so let's do a good old problem from Cal 1. Find the maximum volume of a rectangular box with no lid if it is to be made from 12 square meters of cardboard. Does that look familiar? Find the maximum volume of a rectangular box with no lid. So imagine we're going to make a rectangular box. So it's like a shoebox, something like that. We're going to make this thing out of cardboard. It does not have a lid on it, so that doesn't have a lid, but it does have a bottom on it. What is the maximum volume that we can get from that, right? So first of all, let's try and come up with what is it that we're trying to find the maximum of? Volume, right? So I need a volume function. So let's get a volume function going. Well, my volume, let's label some things. How about we call this side x, this side y, and this side z. I could have used length, width, height, whatever. I'm going to use x, y, z. Then do you agree that the volume is a function of three variables, x, y, and z, and it is exactly x times y times z? That is our volume function. Now, do I have any constraints? Yes.
A box doesn't have the lid.
It
It has to be rectangular.
It has to be rectangular, it can't have a lid, and I have to use how much cardboard? 12 square meters, right? That's our constraint, is that the surface area has to be 12 square centimeters. So what is the surface area of this box? Let's just write it down as area, A over here. What is the area of that box? So we have this front side. What's the area of that front side? X times Z, and then we have a back side also, right? So we have two of those. We have 2xz plus, let's do the sides. This side, and then this side. That's yz, 2yz. Plus, and then one more thing. We have the bottom. Ooh, that's terrible. That bottom side is what? xy. So what can you tell me about this area? This area has to be what? 12. Right? So we have that 2xz plus 2yz plus xy must be 12. Do y'all see that this is exactly what we just did? We have a function of three variables, we have a constraint equation, and we're trying to find the maximum. Now we are applying it to like a physical situation. This would not be possible in Cal 1. You couldn't do this in Cal 1. There's too many variables. Too many variables. The only thing you could do in Cal 1 was, you remember a problem in Cal 1 where they gave you like a sheet of cardboard and they said you're going to cut the corners out of it and then fold it up and make a box? Did y'all ever see that problem? It's a classic Cal 1 problem. If you haven't seen it, don't worry about it. But you can do something like that, but it starts out, they give you the dimensions of this sheet. So you know, like, you already have some constraints, and you wind up only having two variables and you can solve for one and it works out. This can't do with Cal 1. So let's do it. See how fast we can work through this one. Equation 1 is yz equals lambda. Careful with this part. 2z, it has to be in parentheses, 2z plus y. Okay, second equation. Partial of this with respect to y. xz equals lambda, and then partial of this with respect to y.
2z
2z
plus x.
plus x. Okay, third equation.